All right, yesterday we talked about exponential functions. We said that exponential functions were one-to-one, which means that they have an inverse that is also a function. Well, this is the inverse of an exponential function. A logarithm is the inverse of an exponential, okay? And so the definition of a log equation, there is a direct relationship between the two. If you know that y is equal to the log base b of x, then that's going to tell you that's the same statement as saying b to the y is equal to x. Okay. Now, the way you heard me say that out loud is really, really important. We don't say like log b. You say log base b of x. That's how you would read that out loud. So that's really important. It's important because the base is the most important part here. So when we switch these back and forth, here's what you need to remember. Because of their inverse relationship, notice that the base is always the base. So here b is the base of the log. When I rewrite it, it's the base of the exponential. Okay, so that's the first thing. Then the role of x and y switches. And here's what I like to always remember to help me rewrite this. Logs equal exponents. So when I say y is equal to the log base b of x, that's saying if my base is b, what exponent gives me the value of x? Okay, that's how we would interpret this. If I want to switch this backwards, okay, if I want to go from exponential form to log form, the b is going to remain the base, but logs equal exponent. So that's why the y moves out to the front. So let's practice rewriting these. So number one is we want to take the logarithm and switch it to its exponential form. Okay, we're writing it in its inverse form, essentially. So the first thing we identify is what's the base. This is the log base 5 of x. So the base is still the base. And logs equal exponents. That tells me that 2 needs to be my exponent. And then the only thing that I have left is the x. So that would be the exponential form. Will you pause your video, please, and go ahead and try B and C, and I'll come back in 3 seconds with the answers. All right, so for this one, the base is B. Logs equal exponents, so the exponent is 3, and that tells us that it's going to equal 64. And for the last one, the base is 3. It's equal to y, so that's the exponent, and then that has to equal 7. Now we can go in the opposite direction and take its exponential form and switch it to log form. So if I have 12 squared equals x, the base is 12. So I know that this has to be the log base 12. Logs equal exponents. So the 2 has to go on the other side, which means I want the log base 12 of x. So go ahead and take a couple of seconds to try B and C. I'll be back in 3 seconds. So for B, we're going to want the log base B of 8 equal to 3 because it has to be equal to the exponent. And similarly on this last one, we want the log base E, remember E is a number, of 9 is equal to y. Okay, so that's how we can switch back and forth. This is really, really important when we get to solving equations that we're able to move back and forth between these. So this is an important thing to practice. All right, moving along. Using what we know then about how to rewrite them, that is how we're going to evaluate logarithms. So what is important to remember is, like I said, logs equal exponents. So when you're evaluating a logarithm, that means we're trying to find a missing exponent. So you got to know your perfects here, your squareds, your cubes, your different powers of different numbers. So here's essentially the idea. What is this first question asking us? The log base 2 of 16. This is going to equal some unknown exponent for a base of 2. So the part that we kind of think in our head is 2 to some power has to equal 16. 2 to the 4th is equal to 16, so that is our answer. It's 4 because 2 to the 4th is equal to 16. That's what you're trying to find. A logarithm finds a missing exponent, okay? Now for B, we're saying 7 to what power equals 1 over 49? Well, the first question is, how do we get to a fraction if we have an exponent? We know that our exponent needs to be negative. That's how we're going to get the 49 down to the denominator. And then 7 squared is 49, so this is going to be negative 2. And again, why? That's going to be because 7 to the negative 2 is 1 over 7 squared, which is 1 over 49. That's kind of how you need to be thinking this through, okay? So when you see a fraction like that, you know you're going to need a negative exponent. C says log base 25 of 5. So 25 to what power is equal to 5? How do we get this to go smaller? Well, I know that the square root of 25 is 5. And remember that the square root of a is equal to a to the 1/2 power. So in this case, this is going to be 1/2 because 25 to the 1/2 power is equal to the square root of 25, which is equal to 5. That's where we get there, okay? And so similarly on the last one then, how does the log base 2 of the 5th root of 2 happen? That's going to be equal to 1/5. For a very similar reason, fraction exponents make radicals. So anytime I have the nth root of a, that's going to be equal to a to the 1 over n power. Okay, so that's how we know that that has to be 1/5. Okay, here's some interesting log properties, and this has to do with the fact that logs and exponentials are inverses of each other. They undo each other. That's important, okay? So if you have the log base b of b, that must equal 1. Because again, that would mean b to the what power is equal to b. Well, b to the first is equal to b. So if your base matches the number inside the log, it's always going to be equal to 1, okay? Secondly, the log base b of 1 is always going to be 0, because if I want to take any number to some power and get an answer of 1, then that exponent has to be 0, okay? And so this has to do, again, with what we know about exponents. Okay, that's where these are coming from. Now, number 2 is very, very important. So is number 1. These I would definitely put on a flashcard. Those are things you need to recognize immediately. If I do the log base 5 of 5, that's 1. If I want the log base 97 of 1, that's going to be 0, no matter what. Any log of 1 is going to be 0. Okay, now the inverse property is this. A log undoes a base if the bases match, and a base undoes a log if the bases match. This is because they are inverses. So if I do the log base b of b to the x power, the log base b undoes the exponent base b, and we just get the exponent left over. That's all that's left at that point. Similarly, b to the log base b of x power, the b exponent base undoes the b log base, and we just get the x. So let's see what that looks like when we put those into practice. So the log base 7 of 7, again, what we notice here is that these match, so this is going to be equal to 1. That's that number 1 property that we looked at. B, the log base 5 of 1, you need to immediately recognize that that is going to be 0, because of the 1 on the inside. Anytime there's a 1 on the inside, that's what you're going to get. Okay? The log base 4 of 4 to the 5th, the log base 4 undoes the base 4, and the answer is just the exponent that's left. And then for part D, 6 to the log base 6 of 9, The 6 and the log base 6 undo each other, and so you're just left with what's inside the log, which is 9, okay? Now, we're going to talk about the graphs of a log function. They look very similar to the graph of an exponential because they are inverses of each other. So anytime you want to graph a logarithm, you want to start by graphing the exponential that goes with it, okay? So if I have the graph of f of x equals 2 to the x and g of x is equal to log base 2 of x, they should be inverses. And remember, if you start with one function, the inverse is just going to be the x's and y's flipped around. So we'll start by graphing the exponential function, and we've graphed this one before. Again, the easiest way is just to set up kind of an xy table. This is just a parent function. There's no transformations, so we know it has to go through 0, 1 because 2 to the 0 is 1. And then if we plug in, let's say 1, and let's also do 2 for good measure. So if we plug in 1, 2 to the 1 is 1, and then 2 to the second is 4. So we will start by graphing that 0, 1, 1, 2, 2, 4. And don't forget that we have an asymptote at y equals 0. This is going to be increasing from left to right, so the graph looks kind of like this. That is the graph of f of x equals 2 to the x. Now, if we want to graph the log, we're going to take those points and flip them all around. So to graph g of x, we're going to take the x's and y's and reverse them all. So we have 1, 0, 2, 1, 4, 2, because that's how inverses work. So 1, 0 is going to be right here, if it'll let me draw it. 1, 0, 2, 1, and 4, 2. And so my original asymptote was at y equals 0. But remember, with inverses, the role always reverses. So now it's x equals 0, which is now a vertical line. So now our asymptote is here, because everything has to reflect over that line y equals x. So our graph looks something like this. So that is the graph of the log base 2 of x. So that's the relationship between the two. Anytime I need to graph a log, I start by thinking from the exponential. That's where I always start. Okay, so here's some things that you need to know about the graph, similar to the others. This one, the domain is going to be restricted because we have a vertical asymptote. So the domain is only going to be 0 to infinity, but the range is negative infinity to positive infinity. All of these graphs are going to go through the point 1, 0, and they're going to have no y-intercept, okay? And then you can see the rest of that information there is really similar. All of our transformations are going to be exactly the same. Up or down, left or right. Notice the parentheses with the left or right because the vertical and the horizontal look very similar. You've got your reflections, your stretches, your shrinks, and so there we go. So will you take a moment to pause the video and try number 6 and 7 and see if you can identify those transformations before we stop for today. All right, here's what we should have. So this negative is outside of the log, so that tells us it's a vertical transformation, so it's an x-axis reflection. We move left 4 and we move down 1. Now, if you think of a vertical line for an asymptote, that's not going to change if I move up or down, but it is going to move if I move it to the left. So that's why our vertical asymptote now is x equals negative 4. It's going to be whatever your h is, okay? And then on number 7, we have a base of 3. The only thing that's happening here is this is moving up 2. It's not horizontal because it's not inside parentheses. So it moves up 2, and up or down does not move a vertical asymptote, so the vertical asymptote is still at 0, okay? This is where we're going to stop for today on our log functions, and we'll talk about domain in the next video.